So in the last 2 weeks, we have studied several different search trees, namely the AVL trees, splay trees, red-black trees, and B+ trees. So what are they for? What was the main purpose of these trees? For speeding up searching, right? But why do we have to speed up searching? Because we have too many data, or say too many information, right? Put it in the popular term, we have the big data problem to solve. So one of the most commonly used application that is concentrating on searching is what? The search engines, right? We say Google is the biggest, but certainly not the only one. And we have so many different search engines running. So how do these search engines respond to our requests? By implementing a search tree? Not that simple. So today's topic is inverted file index, which is the real key technique used by search engines. And we decided to introduce to you this topic because we consider it a kind of application of what we have learned about searching. But with limited time, we're not going to go too deep into the details, but rather a sketch of the whole picture. So to tell you what is supposed to be done to build a search engine, and how do we evaluate a search engine, like how do we compare them, since there are so many of them, say which one is the best, in which way. So it will be a brief introduction. Now let's get on to business. Well, say if you're supposed to build your own search engine, what are you going to do first? You're going to need a spider. It's not that spider. It's a tool to help you to fetch those web pages from the internet, right? Now with all these web pages stored on your machine, and here you get a request. How can I find in which retrieved web pages that include computer science? And that is the most basic function that a search engine is supposed to have. Now let's again start from a very naive solution. Solution 1, we simply scan each page for the string computer science. Is it going to work? Well, say, wait till your next live. It's impossible given the amount of data we have, right? So, how did Google do? This is a picture I made, say, about 8 years ago. So they have more than 1 billion web pages indexed. That's many years ago. 1 billion sounds like a big number, but today it's 1 trillion. So what does it mean? What does indexed mean? We're going to see later. So solution 2 is, what if we construct a term document incidence matrix? For example, suppose now we have 4 documents, and these are the contents of the documents. And this term document incidence matrix is something like this. It's a 2-dimensional array. Here is a list of all the words we obtained, or say all the terms we obtained from those 4 documents. And each column corresponds to a document. Okay, if this term is contained in this document, then the corresponding element will be 1, otherwise it's 0. So for example, if we are looking for the word fire, we check this row and realize that this is the only place that we have a 1, which means fire is contained in document 2, and this is document 2 is the only document that contains fire. So is it true? Let's check. We don't have fire here, and okay, fire is here in the second document and not in any other documents. So here we have this matrix. With this matrix in hand, It's certainly very simple to search for one word or say one term. How about combination of terms? So for example, let's try to find documents containing both silver and truck. What can we do? We just check these two rows. Okay, for silver we get 1010. For truck we have 1011. A very simple solution is to simply do bit end of both string and consider each row as a string of ones and zeros. So they're like binary numbers. And we just do a simple AND operation to these two binary numbers, and we obtain a string like 1010, which means silver and truck are both contained in the documents number 1 and number 3. So let's check here. In number 1 we have silver truck, number 3 silver truck. Okay, not in document number 4. Number 4 only contains truck but not silver. So it sounds like a very simple solution, right? And what's the problem? The problem is that this matrix can get very sparse. Sparse means it contains many zeros. So it's going to be a big waste of space and time. So what's the solution? How are we supposed to improve it? Use linked lists instead of a simple matrix, right? So here comes our solution 3. It's a compact version of that matrix solution. It's called inverted file index. First, let's define the index. Index, we say, is a mechanism for locating a given term in the text. What does it mean? It means that index is like a kind of pointer. So what is a pointer? Pointer stores the address of something, right? The position of something. So index means to store the locations or the positions of the given terms in a text, right? And inverted file is a file that contains a list of pointers. Pointers means positions. For example, the number of page to all occurrences of that term in the text. What does it mean? Well, let's check out this example again. Okay. So this is a list of files or documents. The inverted file index looks like this. First of all, we have a list of all the terms. And for each term, we maintain a linked list. For example, for this term A, we know that it appeared 3 times. Okay, and it's in the documents number 2, 3, and 4. So A is in document, not in document 1, but in document 2, 3, and 4. It's called inverted because it lists for a term all the documents that contain that term. Okay, a normal file is a list of documents like this. For each document, we can maintain a list of terms it contained. Inverted file contains the linked lists for all the terms. So that's why it's called inverted. Okay, now here's my question 1. How to easily print the sentences which contain the words and highlight the words? If you think about how we use a search engine, when we input one word and click on search, in return, the search engine will not only show the document number or say a link to that document, but instead it shows a piece of sentence that contains that word, right? And with that word highlighted. And how can we do that? With this inverted file index, we can only tell that which term is contained by which document, but not the positions, right? If we would like to tell the positions, we need to record something else, right? So here is how the real linked list look like. Well, here, first of all, we need to record its frequency. It's called times. For example, the term gold appeared in 3 documents. Okay, 1 means in the first document, it's at position 1. It's the first word. So let's check. So indeed, gold is the first word in the first document, right? And in the second document, it's at position 3. It means that in the second document is 1, 2, 3 is the third word. Okay, so we have a linked list that each node contains not only the document number but also a list of positions. And that position may not be unique. For example, silver in the document 3, it appeared at 2 positions. Let's check document 3. It's silver here and here. It's at the 3rd and 7th position. And so altogether, this is called a term dictionary. Within this term dictionary, for each term, we maintain a posting list. This is called a posting list for a term in the term dictionary. The second question is, why do we keep this times, or say frequency, in this posting list? Why do we need this? Well, think about this. If we're merely looking at one term, that frequency is useless. But if we are looking at a sentence that contains several terms, then we are supposed to find the intersection of all their posting lists, right? For example, if the input is something like truck, silver, and delivery, what's going to happen? One solution is that we just start from the first term, truck, and check its posting list. Okay, and see truck appeared in document 1. Is document 1 also in the posting list of silver? Yes. Is document 1 also in the posting list of delivery? No. So document 1 is not counted. Let's check the next one. Document 3. Is document 3 contains silver? Yes. So is document 3 contains delivery? Yes. So document 3 is okay. Now let's continue to check for document 4. But at this moment, you already know that 4 is impossible because there's only one document that contains delivery. So it's not necessary to check other terms. However, your computer would know, right? To let your computer know that, what are we supposed to do? So when trying to find the intersections, we better start from not from the one with the highest frequency, but start from the one with the lowest frequency, right? If we start by checking delivery, we only have to check it once, right? In one run that we can obtain that document 3 contains all of the 3 terms, and therefore make it faster. So the key is to generate the inverted file index, so-called index generator. That is the key part of a search engine. And this is an extremely simple pseudocode description of the whole index generator. So we're supposed to first get the spider to fetch all the web pages, or say all the documents, and then enter this while loop. While we are reading a document one by one, for each document, we read the document term by term. So while we are reading a term, the first thing to do is to check out if this term is already in the dictionary. If this find function returns false, it means that this is a new term. Then we insert that term into the dictionary and create a new posting list for this new term. Okay, if it's already in the dictionary, we skip this part and get this term's posting list. So basically what we do is we should update its posting list by inserting a new node to this term's posting list. Okay, that is to insert this document into T's posting list. After we're done with all the documents, we're supposed to write the inverted index to some disk storage. So this looks really simple, right? So what are the difficulties? What's so hard about implementing a search engine? Well, there are several key modules to consider. First of all, read a term in the document. How are we supposed to know that a term is a term? Well, the difficulty is language dependent. If the language is English, it's a little bit simpler because you see all the words are separated by spaces. But in Chinese, it's going to be really hard. For example, I once searched my name. My name is Chen Yue from the internet, and I obtained some results like 酒并非越陈越香. So you see the point. This is the first difficulty that we have to deal with. And so there are a group of people working on so-called the token analyzers. Token is just another name for term. Okay, so it's like term analyzer with stop filter. We're going to come back to stop filter later. And the second part is find. Okay, to search for a term from a dictionary. That's where we need those searching techniques, those search trees. Okay, so we're supposed to find a term from a huge dictionary quickly, and that is the module vocabulary scanner. And then if it is a new term, we have to make an insertion, and this part is called vocabulary inserter. Basically, these are the two modules that will involve search trees, or not necessarily the search trees, but also think about other methods like hashing. Okay, anyway, there are many people doing research in these two areas. And finally, since we're talking about big data, it's not a small data, and therefore, the amount of data is so huge that it's definitely impossible to hold everything into our main memory, and therefore we have to write the inverted index to a disk storage from time to time, and therefore we need memory management. Okay, so basically these are the key areas that people are working on, still trying to make improvements. Then we're going to talk about these four modules one by one.